Right, so for the last lecture, we're going to do two things. Right, so the first is to pick up what we just left off last week. We're going to finish the text mining lecture by the subtopic, so we knew the training technique of structured topic model. And then we're going to do a quick wrap up of the topic throughout this semester. So that's a way to conclude this course. Right, so we just go directly to this. Right. So from last week, you have learned topic model. So what is structured topic model? So, well, that was pretty much any article or piece of writing. The document may contain multiple topics, as you know from last week. For example, say it had estimated topic, document distribution, and conditional on the term topic distribution, and after that you write the joint distribution of all this to calculate the probability of if we pick the document and the probability that the joint probability actually, the document would be related to the particular topic. So what's the probability? So we know that, okay, so a document may contain multiple topics and use different proportion of words to represent those topics. So that it's related to a particular topic with different probability, right? This is how the joint probability is calculated. But more importantly, what's the proportion of text allocated to a certain topic in a document? And more importantly, if you eventually become more proficient at retrieving those information, for example, some people, I think like some of you are very good at writing those crawler function, or I think that there's a package related to Python called Spider, right? Crawler function to do web crawling to retrieve those pieces of information from news article or internet forum, right? And for each piece of text, it contains multiple information, which we call document level information, or document level variable, or some people that could use the trendy word called meta level information, or meta information. So what are those meta information? You can say the author's ID. So for example, some author are noted for their extrinsic personality, or they tend to appear only during midnight, or their writing tend to be more liberal, conservative, even aggressive, or exudes a sense of xenophobia, or some kind of value or something, where it can be extremely partisan to a certain party, right? There are other document level or meta level information, for example, like the IP address. For example, I use that quite a lot to delete those repeated accounts. For example, a person might register a multiple account in order to lose his post, right? And these are people that we need to get rid of. Right? So I wrote a function to detect those repeated based on this IP address. Of course, you can definitely fake your IP address by simply use those sheer Wi-Fi address of your change all the time. Also, there are some your longitude, latitude position, your geolocation, right? So, for example, people you can actually detect from those information about where you are currently when you try to post this to upload those posts, right? There may be other information, for example, the time at which the post is made, or for example, like tag, right? Because nowadays the news industry urgently asks people to tag keyword related to the piece of news, so that it's easier to organize and to retrieve data. For example, if I want to see a news related to a certain politician in the past 60 days, I simply use the text as one of the keyword from my retriever from my inquiry function, and then I just fit this attribute to my inquiry function, and then they will retrieve any news related to that particular politician to me. That's easier. So the purpose of this model, which eventually this author wrote into a package, is called structured topic model. So just like topic model, we estimate the probability that the document is related to a certain topic and its term distribution across topics. But we also aim to do two things. For example, calculate the proportion of word in a document that's related to a certain topic, so that you know a document is more associated with a certain topic. And then I think it's one of the most innovative thing for this class of model is that it allows you to use some not just word or term distribution in a document as a predictor, but also other metadata information that you can use as your right-hand side variable. So it's pretty much like you're writing a linear equation, for example, like your LN or GLN model. You can use any meta level information, document level information as your predictor. Right-hand side variable to predict the distribution or the proportion of topic in a document. So we also provide a handy application function. So that's very easy and also very handy, I think. Right, so that's it. So as with pretty much any piece of writing, a document has its own structure. So what is structure? We can say topic prevalence. So we can say a document is more related to a topic, right? If you remember from our past week's lecture, simply take a look at this piece of text. It strengthens the U.S. economy or could be an important factor when going ahead to the poll later. According to U.S. Treasury Secretary Lyndon Johnson, and despite anticipated cascading economic impact of coronavirus outbreak. Right, so this piece of text is a really short piece of text related to more than 3 topics, talking about the state of the U.S. economy, the county presidential election, and its physical effect, and also the coronavirus, at the height of coronavirus. So again, probably a little more than 3 or 4 topics. But you allocate this proportion length of word to talk about economy, right? So I say this piece of text, at least from my own perspective, is more related to the state of the economy than politics per se. So we can when doing text mining, we should try to identify what's the topic proportion in a piece of text. So how much of the document is associated with the topic? How much of the word used in the document is being allocated to a certain topic? Also, the topic content, the word used within a certain topic. So what are they? How are they distributed? Can we visualize them to give our reader a clear sense of their distribution? Also better leverage those metadata which we haven't been able to incorporate in conventional text analysis. For example, author's name, social media site, you can say, well, some social media site are extremely well known for its liberal value or something more conservative. For example, you can see that the social conflict in the U.S. in the past 2 days, the debate over Roe and Wade, whether women should have the right, according to her will, to seek abortion, right? Social media side, or some conservative side say, no, you can't, right? Because they're more pro-life instead of pro-choice. Also, the number of subscribers, if you're trying to analyze social activity of this YouTuber, then you really want to track this number of followers of this YouTuber, or the post positive and negative sentiment rate, right? So we can better use those information to help us predict either the topic distribution, the term distribution across topic, also the topic prevalence in the piece of text. So for the structured topic model, we introduce a new algorithm for estimating of this. So how is this achieved? Right. So in the assigned paper for those three, the Matthew Robert and her co-author provide a paper on this. So they proposed a measure of topic quality that combines sentiment coherence and exclusivity, which is a weighted harmonic mean, he said, the inverse of the frequency distribution. In terms of a word's exclusivity and frequency, so that's where this measure, the abbreviation of this measure comes from. Co-tracks. Right? The frequency and exclusivity. So how is this measured? So the term D is simply an indicator to be that is the number of times that any word VI and VJ appear together in the document. So you have to calculate this the probability that there's two or any pair of words that co-appear in the document. And then for a list of n most probable word in topic number in topic K, in any topic K, the sentiment coherence for a topic meaning that, so here the measure for coherence meaning that all a list of words appear, if they co-appear in a document, in a document meaning that, well, the document is more likely according to the structure of this, or because words that more frequently appear, we probably infer something, right? They probably mean something, right? For example, you try to convey a message, the message probably has a higher likelihood of containing a list of words, right? So you have a higher probability of detecting the high frequency distribution or a high number of this list of words that co-appear inside the document, meaning that the structure of the document that is more likely to be related to a certain topic. And that for any period document that contains this word, they're probably more coherent. Their message will be more coherent because they contain sensitive word. So the coherence is measured by this new measure called frequency and exclusivity, which is just the weight assigned to a word in J document by covering a potential K candidate topic. So let's say the K topic is just the weight over the empirical distribution of the probability that we should find. If we randomly take the word D out of the word W, that is a K topic, plus the 1 minus W, the weight given to the word in J document of K topic, over this empirical distribution. So that's how it's defined. So talk about the application side. So structured topic model, you provide any text processor function, or that is from my perspective, I think it's a very handy function if you primarily analyze English language. But for our language, you might require some sort of reprocessing. For example, you need to get rid of those documents that contain missing value or empty cell because because text processor is written in English, so you probably wouldn't be able to read those words, and they were throw you an error message. But for English text, you can do this with relative ease. But you should not be discouraged from applying the skill on Chinese text, for example. Because the most important thing is that you need to have your original document, and they should be well indexed, right? So that the text processor function can match on the index and to find out the word distribution in those documents. So that you should have pay attention to those pre-processing tabs. For example, remove those documents that contain no information, and then try attention to those strange characters because you might not be able to read it. So that you can by doing so, you can easily render the task and metadata of the document into separate data. So for the argument that should be placed inside the text processor function are list of vocabulary, as I said. So you actually have indices for each word used in a document and spacing distribution in the document. So that they should be mapped onto the original list of documents. And also some metadata information, the method level data information, the document level information, and you should organize it into a different-ish object. So that will allow you to infer the topic of the document using tags, which should be rendered into an LDA project before processing, and then you feed the LDA object fit into the text processing function. So that you can use the tags and then some other metadata as predictor, just as you would when writing a linear regression model. Just use plus sign and keep adding variables in your metadata as a predictor to predict the term distribution. So, which I will demonstrate that real quick. And for visualization, you provide some very intuitive plotting function like content, plotting out the content of the topic, and also how the topic and word are distributed across this document. In the perspective plot, perspective means that with respect to the topic, trying to show the distribution of term in the topic. So here we were just an exercise on this. So we were switched to our RPOP for some exercise. So here I want to use my example from my recent work about international armament collaboration. We all have witnesses to the Russo-Ukrainian conflict, which I exercised throughout the semester, and you see that there's a bunch of weapons that are being used, right? And among those fancy high-tech weaponry, we can actually see some collaboration patterns. It seems that the U.S. the United States is getting relatively well with its core ally. So who are those core ally? The U.S. core ally. For example, like UK, right? Due to the MOB, they have a special relationship. We emphasize their diplomatic argument. And they will be English-speaking countries. So the U.S. also shares some close affinity and in terms of diplomatic relationship with Australia, right, and Canada. And this country, they are the largest, the most important donor that supply arms to Ukraine, right? And also some of the weapons are used, so they have shared commonly between these nations. For example, they use the US and UK, and Australia use many of the same weapons. Well, that's because there exists, say, they're strong diplomatic and strategic type. They kind of push them toward armament collaboration, so that they collaborate and pooling resource, financial technology resource together to produce more arms. So we can actually easily plot it out into a network object and visualize it to the computer to get a clear sense of how this relationship type is. Right? Well, I have to say I kind of regret that we don't have enough time to cover this one additional topic about the network analysis, which I intend to cover at the very beginning of this course, but since we actually don't have enough time. So but that's very easily done. You just you need a IGRAD package. We'll talk so you assign US as the central node, and it seems like, okay, so this is that we collaborate with the 7 key allies, and some of them are, I would say most of them are NATO countries, but there are some other key allies. They are non-NATO country called MNA, a major non-NATO ally, MNA. You see that? But however, it should be noted that not every NATO country have the probability, have the chance, or they have worked alongside the U.S. in terms of armament collaboration. Because there's one key factor is missing. Is there technological prowess? Because for some countries just don't have technology to contribute, so that the U.S. will not sit in as potential collaborator in terms of weapon technology. So we see that for a country that's at the core of this means of collaboration are usually also countries that are well known for its heavy industry or high technology powers. So building on this understanding, we were I collected a set of international armament collaboration related news article and official document, and I organized into a spreadsheet, which I actually put it on a CSV file. And drawing on this rich collection of document, I just analyzed also the pattern of collaboration among between the U.S. and its ally. Can we infer some interesting pattern of some interesting relationship pattern from this text? So here's what I did. So before that, we need to load and require the STM package, and then we need to load the data. So in order to feed those data into text processor, we become the backbone of our STM analysis. We need a couple of things. First, we need the original document, which will serve as our metadata, and also we need to process the word indices and also its recent distribution, and this vocabulary. And the indices need to be matched onto the original metadata. So to do that, you can simply apply the LDA function, which I introduced last week, and then you should produce actually 2 objects. So there are 2 elements inside an LDA object. So the first is just indices of word used in the corpus in this document, and so it's previously distribution. And also a list of vocabulary. So you only need these 2 objects, so in order to proceed. So we can take a quick look at what's inside the original metadata, which is our list of document. So you can see that we actually have 287 original document. Well, actually the original number of document is about 330. But of course, because some of the weapon project actually multi-nation collaboration, so that they are repeated, right? For example, like the 35 strike fighter, the Joint Strike Fighter program, it's a collaboration of more than 10 countries, but under a prevailing armament project. So it's only counted as one, right? So there are 287 unique web projects, and you contain 5 variables, 5 columns, which are text and the direction of technology transfer, whether it's from US or maybe the US acquired the technology from other nations. So if the original military technology transfer is from the US, then you will be called as 1. If from other country to the US, then you will be called as 0. And here is a numerical measure of the alliance strengths. Also the differences. So the difference in calculator technology capability, the differences in their technological capability. also the transfer type. So they had co-development or sourcing or other type of collaboration. So we can simply take a few lines of text to see what's inside those documents. So we would take so we can see the first 3 rows. So the first row, the first one has the first row of text is the UK is the sole tier 1 partner to find the development of financial commitment each partner made. Although inside it contributes to the development of the Joint Strike Fighter program. While the second document talks about the Italian contribution to this fighter jet program. You can also see that if you simply use the hat function to look at the data, it will also show you the meta level data, right? Because the first column is the text, right? And the second column is the direction of their technology transfer. The third column is the measure of their aligned strengths. What difference of being there, the difference in their technology capability and transfer type. Using the numerical indicator. So we can also check out what are the class of this data format. So the LDA class is just a list, right? And it contains 2 elements, as I said. The first is just a document indices. The second one is the list of vocabulary. So we can take a look at the first element and also the first column. And one column actually. So you see that the document element inside the LDA object, which I named as ICLDA, is just a document of the list whose length equals the number of documents that we collected. You need to pay attention that number of documents should have the same row length with the metadata that fit into the model. Otherwise, it won't fit. It will throw you an error message. And each element is integer matrix with 2 rows. Here you see this is 2 rows, right? And each column of the document represents a word, a 0 index or identifier for the JSON document. So this one is for the JSON, the first document in a collection of documents. And each column means a text. Means a word used in that document. And the first row is a 0 index or identifier. So you begin with 0, so you shouldn't be any. So what does the 0 mean? Because as you see in my note here, the second row is an integer denoting the frequency that the word appears in the document. So there is a word that appeared twice in the JSON document, but I mean it's zeros. What does that mean? Well, because the indices begin from 0. There's some programming language uses zero indices. For example, like Python actually uses 0 indices. So to count from the first element appear in a certain list of data, all the way to the tens, you should count from 0, 1, all the way to 9, instead of 1 to 10. Okay, and so. Then take a look at the second element, the vocab. Vocab is just a character vector specifying the vocabulary word associated with the word indices here, used in the document. So if you take a look at the vocab and show the first 10 vocab, you see that, okay, so it's just this word, the collection of word, character vector specifying the vocabulary word correspond to this. Right? So you see that the first one is just the dash bar you use twice in our code. The second one is the comment. Okay? You also use twice in this string of text. And now the most exciting part is prepare a document, and we need the following 3 objects. First is the LDA the document element of the LDA object. The second one being a vocab element from the LDA object and your original metadata. And then to save on typing, you don't want to type that many, but you want to do subset, you just rename it, but be sure you know what you were doing, right? And then, as I said in our slide, we need this following variable, and then we need to convert it into a factor variable. So we use S factor to convert it into factor type. Then, as you have been familiar from last week's lecture, we need to have some intuitive sense about how many potential topics are in the document. So actually, the STM package provides a handy function for this called search K. So you will search for those topics for you. You will identify the ideal number of topics for you. So the first argument you use is just the document, and the second is that there's a vocabulary, the vectors, or there's a vocabulary used in the document, and then specify your function. Use just some right-hand-side variable that you're going to use, and then you will search you will estimate the optimal, but you would actually decide the optimal number of topics that would better classify this document, around from 2 to 15. So if you are not happy with this range of topic, you can probably use a wider distribution, say 2 to 20 or 2 to 100, but of course, they're not making longer to run. So based on my experience, I would say somehow like 2 to, but however, it must be larger than 2, right? Because it's all related to a single topic, and it just won't work. Based on my experience, I would say anything around like 23 to 25 should work. So you shouldn't do like 2 to 100 topic. You shouldn't run around a search K function for 2 to 100 topic. I think normally like 2 to 23 or 25 should work. You probably would just stabilize. The algorithm just stabilize, and then you can plot it out. So here, just for pedagogical purpose, I choose to estimate a 10-topic structured topic model and use transfer type as our outcome variable as our outcome variable to store military technology hierarchy into topic classification, and we set the next iteration, the MC process, multi-column. Process to just to 1,000, so that it wouldn't take very long. And then just fit into the STM function. The first document should be document, the second document should be vocabulary, and use the numbered document that is set for this estimation. So previously I said 10, right? And specify there's a variable you're going to use right here. And you're going to estimate iteration, your data, you should just use your metadata, which are defined previously. Then you will create an STM object, which you can plot it out. But here, you should note that the label are actually assigned by us. Right? So, to do this sort of analysis, I would recommend that you first plot this STM object using the summary. So we create different type of plot. Summary plot, perspective plot. So summary plot will just show you the distribution of work across the number of topics that assigned values. So here you will show distribution of work across this 10 topics. Right. So the topic that is at highest, right, should be the topic that will be allocated the largest proportion in your entire course. So you say, so I would say about my collection of document, this type of topic which I name, right, that is not assigned or assumed by the STM function, is actually named by me because based on the distribution of work which I infer to be something related to aircraft engine, right? See that engine, power, electric, GE, General Electric, right? It's the power plant manufacturer produce. But of course, you might not be happy with this naming convention. You can say, it looks to me to be nothing, so you can name it as nothing, right? Or just bullshit, right? But by I mean, the good thing is that it provides you with such flexibility, just use the topic name, right? So I would recommend that you first plot it out using the summary plot and to see how this word are distributed across the number of topics that you assign. And then you can determine what should be the appropriate label for this topic. And then you plot it again, call the topic name, and name it according to your preference. Saying that would be the best best way to do this. So we can clearly tell this, right? So the topic related to aircraft engine, they command the highest proportion of tasks in your production document, followed by government contract, and then partnership, sensor, right? You can clearly tell, like, or like pod mission sensor are related. Sounds related to sensor. While armor, turret, protection, and technical, they are terms related to the ground system vehicle. For example, the turret. So let me repeat that if you guys are not here. Draw a pen, right? So for my orbital drawing skill, and this part is the turret. Right, so by simply looking at this, you intuitively know what this test are about, right? They're related with the topic that they're related to. Also, the missile defense, ballistic, right? Ballistic missile defense, consortium because they need to collaborate together. So now we have some intuitive sense about how this document is all about and how the topic is distributed across. But then we can. Oh yeah, I forgot to state something about it. The label type, how are these words distributed? So the most recommended method is the FRAX, right? Frequency and exclusivity measure, which is also part of their methodological contribution. So I tend to use label type. I set label type to FRAX. So it's a metric that is used for calculating how the word should display. So what word should be retrieved and be displayed on the wall. Right? That is the number of words. So for the end, I specifically, or because we need to save on space, right? So I only need the top 5 words. So if you stick that word, you have, or if somehow you manage to make it a really long graph, so we have more space to accommodate more words, and you can set them to 10. Okay. So now we're showing a different type of plot. So the topic content can be, the content means the term distribution. It could be a function of direction of military technology transfer. So we can do that, right? So we use STM function to estimate once again, right? But here, the only different argument is here. The content, which is an outcome variable, means that the term used in those documents. So here, I tell R, they should be distributed as a function of the form of collaboration, which have 3 types. And then we can plot it out, right, using the perspective plot. And previously I showed the summary plot, but here you can use the perspective plot. So perspective plot is very useful when you, for example, you try to analyze something that where the word, are assumed to be distributed according to some distributed on opposite side of some scale. For example, you try to measure the word used in some legislative debate, for example, like the road and weight debate over the abortion right. So you might map those words onto a scale on the political ideology scale, for example, so liberal, conservative, right? But here, all I care about is whether the original measure technology comes from the U.S. or from its ally. It's collaborative. So here I use a binary indicator to denote whether technology comes from the U.S. or from its ally. So the two U.S. means that from ally to the U.S. But use perspective law. So here's the perspective, because you assume that the words are distributed on the opposite end of this scale. And I asked it to display the top 50 word and choose topic 2. So what is topic 2? It's government contract. So you can also label the scale, the perspective, and also give it a title, the main title of ownership. So you will set the label display on the left and right and of the horizontal axis. So you will show this. So how is the word used? Mostly used in public safety distributed. So missile defense, or suppression, they actually use more distributed toward U.S. allies than to the U.S. But for Asia's radar, it's very clear that, well, because the U.S. is obviously the only country that's capable of making this particular type of equipment. Also, it's named by the U.S. defense company. So you see, most words are actually distributed, even though their frequency does not appear to be that many, because you see that the font size of the word is quite small. But they are almost exclusively distributed on the U.S. side of the wall, right? We also show armor, where is the domain of military technology where the U.S. is almost European ally, hold comparative technology power. So they are more evenly distributed. We also see aircraft engine is more tilted toward the U.S. side. The U.S. comparative advantage in this particular domain of technology. So we can estimate another big invention about the technical valve is that we can estimate the relationship between the metadata, the document level data, and the term used in document to predict not only the topic of, let's say, the topic of the document, for example. What's the effect of some meta level or document level variable on the probability, which is a multinomial probability distribution, that the document is of a certain topic. So we can actually estimate the effect of both term distribution and also the document level variable, to estimate their effect on the probability that a document is of a certain topic, just as you would do in linear regression. So you can see that. So here we use the estimate effect function. Right? So it's just a linear regression model, right? And see the form is just like what you'd be familiar with, the LNGO form, right? So for topic 1 to 10, which is our total number of topics that we assume that their assignment probability can be estimated with this function, right? But you need to use your previously fitted STM object, let's say in the third argument. Also, you need to supply a metadata, and also you use supply a matrix for the uncertainty estimate. So you create an object called prep. And we can subset it to see, okay, so we want to see the the estimated effect is a variable on the probability that the document be assigned to topic A. So you see that, okay, the from, this factor variable, whether the military technology from the US and the transfer type 2 are significantly correlated with the document being assigned to topic A. We can also plot out the effect of certain variable on how the document, how a topic is positioned. So here, we need to simply use the previous-generated trap object here, and use we only use one variable. So whether the from is a vector variable, denoting whether the military technology comes from the US, and we estimate the impact on the color 10 topic. You see that conditional on the military technology being originally from the US, what's the probability that a document will be placed on certain topic? And then we can manually set a label for this topic. So we see that, or if the technology comes from the US, then also we also provide the 95% confidence bound, right? Confidence interval. So we can clearly tell that if the military technology is originally from the US, then the most salient topic that's uniquely identified with US source technology is Aegis radar, right? Or for system integration, armor, they are more likely to be related to technology coming from US allies than in the US. Or for aircraft engine, it seems that okay, it's probably more likely to come from the US than from its European ally. And it's the same thing with partnership. Okay? Usually, because for most of my data, they're usually the direction of the collaboration version are usually the US saw collaboration from its European partner. So partnership are mostly that one direction. Okay. So this concludes our text mining, and so we're going to take 5 minutes break. After that, we're wrap up our course. Right. So we did a quick course wrap up to summarize what we learned throughout the semester. We go from linear regression to variable selection technique to model binary outcome. Algebra and classification model, we dedicate much of the effort for a couple weeks. And trend test split, the larger trend test split, prediction accuracy, we have used quite a lot of text minings, included with text mining. So, linear regression model can be summarized to the following property, which you will be all familiar with, the Gauss-Markov theorem, blue. So what's blue? Blue refers to the efficiency criteria, meaning that you use the variable to predict to explain the largest variance or having the minimum error. So in other words, it means that you have a combination of variable that produce an estimate of error with 0 conditional means, and the conditional the error term conditional on there's a variable including to it is expectation. This kind of value is just 0, right? So it has a minimum variance compared to all other variables, so it's best. The linearity assumption meaning that the outcome variable is just a linear combination of your explanatory variable you put on the right hand side of the equation, but we should also note that if some x variable, all the transformation, or for example like multiplication or square, quadratic term, or a combination of all the explanatory variable in this condition, in the other condition may be violated. Here, the or for example like interaction term, right? Say the fat of x on y is conditional on, say, x2, right? And then we will say their relationship between y and x1 is not exactly linear. Okay, we'll get to that in a couple minutes. Unbiasedness. Unbiasedness requires that under repeated sampling, then the expected value of the simple statistic produced by an estimator, beta, will equal the true value of the population parameter, which we don't know, right? But I only say that with perhaps large amount of sample on the repeated sampling, we should get to the true value, true population parameter. Estimator. A good estimator is one that average close to the population parameter with high degree of certainty, meaning that the estimate statistic have low mean square error, or root mean square error as well. Okay. And there are a couple of metrics to evaluate how good your model perform at explaining the outcome variable. So you should have lower mean square error, meaning that it has less unexplained variance, which is the error term, must be backed out in error term, or high R squared, meaning that more variant, proportional variance explained. You should also know the bias variance trade-off. So if you so let's not forget about this, then you should go back, take a look at the handout or the first couple of weeks lecture note. Now we get the functional form specification, because not only do we want to know whether x has some statistically significant relationship with y, but also want to know in what way is s related to y. So if I want to approximate, you're going to use approximate because it's just we actually do not know the underlying relationship between x and y. We can only approximate that. We can approximate the relationship using polynomial Taylor series expansion, which capture where, for example, at which now does the effect of x and y change sign. Right, you can see, okay, so at the first null, one, the effect x and y change sign. This number 2, that is change sign again. Or you might want to use spline function, which is the local regression. So we have polynomial low e's or spline function making, and using that to make xy relationship looking more smoother. Right? Or an interaction term, which is so for example, the effect of x and y may be nonlinear, additive, conditional on some other variable there. And as you have seen it in our second assignment, I asked you to answer. If you want to include the interaction term in the models, or what should you also incorporate this feature term, for example, estimate the relationship between y and x1 and z. You should also include the constituent term x and z. It's because, well, the value of it also depends on the value of this respective constituent term. The respective value of this constituent term. So that we should also include the value of a constituent term into the model specification. One-time encoding, they include a distinct class as a dummy variable in their own single column. For example, if you have, say, three flavor ice creams, say chocolate, strawberry, vanilla. Then use this one hot encoding. You erase the original color to make this different flavor into your own color. Okay. So select chocolate, we can has its own column, and then strawberry, vanilla, and for those observations, the pink chocolate that will be coded 1, those did not become 0, right? And then do the same for other one hard-coded variable color. Now get the variable selection. So how to select important feature from the data? From the data that contain lots of variables. And for some of them, we actually do not have any information on it. So the traditional way is to use the principal component analysis, PCS, and decomposing the total variance into major component, and then relating each variable to this component. So that's one way to do it. Or you can use the more traditional stepwise selection. For example, forward selection, add variable 1 at a time to see if the added variable have a reduced MSE than the previous model, or to use backward selection. For example, you can remove variable 1 at a time until the deleted variable no longer reduce MSE is the point where you should stop. Or to use the lasso, which I covered this method. This is actually the selection operator. The lambda parameter is used to impose penalty so that a larger lambda will accelerate the penalty, impose larger penalty on unimportant variable, so you'll be kicked out. Right? Small lambda means that more variable will be kicked. Right? So as lambda increases, that's the variable remaining. Now lambda, of course, you use L1, it's absolute value regularization, but you may have trouble identifying unique value, so an alternative would be ridge regression. Also use lambda to impose the size of magnitude of penalty, and use L2 regularization to use square term. And or you want to choose the middle path, and less than that is what you can consider. To integrate both L1 and L2 regularization, and use the alpha parameter to determine the weight allocated to L1 or L2 regularization. So in the model, in the elastic map, the weight is determined by alpha, right? So if you have higher alpha, of course, alpha is blocked between 0 and 1. Higher alpha means they allocate more weight to a lasso. Lower alpha means this weight tilt toward ridge regression, which use L2 regularization or use L1 regularization. Okay, the model of binary outcome. Logic improvement. They are regression model of binary outcome. So logic related effect X to Y using logistic distribution. And this effect is measured as the log of the R. Right? So we spend quite some time talking about this, try to demystify this measure. Right. So, and you should note that because in binary outcome, the outcome of 1 versus the outcome of 0, they are just complementary probability so that I can use log of the R means the probability of something occurred, right? To capture this complementary probability. So as 1, as the probability of 1 outcome increase, the other should decrease because they are complementary probability, just like we were playing with seesaw, right? Or prove it related effect X to Y using uniform distribution, not logistic distribution. This effect measure as marginal probability. And you can use other statistical package to calculate marginal probability. And also, let's specify the system the equation model. So you have multiple equations, right? For example, the parameter in one equation is estimated from another equation. Let's give this example. For example, the probability that Y is a function of a vector of variable plus estimated value of x2. First, as you're working down the line and so looking down the line and continue to learn statistics, you will probably encounter a lot of models like this because system equation, right? System equation, which some estimator on an estimated value from another equation. And for that, you need to pay attention about the distribution form of those equations because for sometimes equations that follow different form of distribution, they cannot be used together. One typical case is that some people use ProMed as their first stage estimation and then insert estimated value as estimated for the first stage estimation, which they use logit, and you cannot use this because the distribution form are different, right? That's totally wrong. For example, in a Hackman regression, there's a Hackman regression called estimated selection effect. So the first stage equation is usually they use a continuous variable, so which is just an order regression, while the second stage regression is ProMed. The ProMed follow uniform distribution, and that should work because well they all follow the same form distribution. But if you use logit, the second stage distribution, then they won't fit. Now the support vector machine, the supervised learning algorithm really has clearly defined label, right? So we first define the supporting hyperplane SHP that classifies data point based on some observer features, so that you would define supporting hyperplane to sort each data point to different class. But however, one thing that people would just jump from linear regression model or parametric model to support vector machine. The one thing that they found uneasy or hard to understand is that contrary to the standard error, in which we want standard error to be as small as possible so that it's very easy to get significant for a preferred variable. But for support vector machine, we want support hyperplane to be as wide as possible so that we are more confident about separating data to different classes, right? So modeling the baseline model, sometimes you can consider treating the hyperparameter, the gamma and C. So C is just a cost function, but it provides soft margin, right? So that larger C value means narrower margin because you want it to be impose greater penalty, greater cost on incorrect classification. So you have narrower margin, but it's very easily violated. Or you can select smaller C so that you impose less cost on incorrect classification. So it's a wider margin, which will have risk of also including other different incorrectly classified type. Or gamma just define how far the influence of a single data point reach, so that low, because it's translated through the C function, so low, so the interpretation just should interpret it the reverse fashion. So low gamma means the far reaching. For example, if you have a data point that belongs to a different class, then the region you define, you assign to another class. If you have low gamma value, then you will have more far reaching. You have more far reaching influence. And that's why you usually see the curve or the band in the separating supporting hyperplane. On the other hand, if you set gamma to be a some higher value, then its influence region will be smaller. Okay. So that the curve, the separating point will be the last curve. Right, there are other different methods, for example, naive Bayes. The classification technique based on Bayes theory with the assumption independence among predicted right-hand side variable. So the posterior distribution of outcome variable is just a multiplicative product of the likelihood function of the theta given no flux. Likelihood function. Of the theta given no flux divided by the prior distribution of flux, which gives us the posterior distribution of computation given predicted. Oh no, in the data, sorry about that. Prior distribution of flux. So which gives us a posterior distribution of flux given the data. So it's relatively easy to perform, even though this independence assumption can be easily violated. So we can definitely adjust that with different methods, which I demonstrate fast. Right. But regression tree-based model. Compared to linear regression model, which is just globally estimated on full data, regression trees built through a process called binary recursive partitioning. It iteratively split the data into smaller groups based on the most salient feature. A simple regression and then a simple regression model is the one using various regression models fit to each branch of the tree. So generally, we typically grow a very large tree and then use cross-validation to pruning back to find the optimal number of subtrees in order to reduce overfitting. There are different variables. The booster aggregate go back in average estimate across multiple subsets, both to reduce the variability of any single tree. And as a way to also reduce overfitting, but then we still suffer from tree correlation. And then random forest is just a modification of backing. You build a large collection of tree decorrelated through bootstrap into multiple subsamples, but estimate only a random selection of n feature. So that each tree that only estimate a slightly different feature. For example, you select a total of n feature consists of this following 3 variable, right? And then for the first tree, you only randomly select 2 features out of total of n features. So you use x1 and x2. And for the second tree, you might use variable x3 and x3. The third tree, you use x1 and 3. Right, so these are just red selection feature. So they're the correlation, decorrelated. The gradient boost machine is an award-winning algorithm that we build on a single relative shadow and weekly learn tree, with each tree learning and improving from the previous one, just connecting those weekly learn tree together to gradually reduce the remaining model error. So it takes lots of time, and as you're working on or the first assignment, if you run the logistic version of gradient boost machine, you see so after the model converge, you probably see a quick note provided by R, say 8487 tree used. Right, this is the number of tree that used to achieve the optimal performance. Okay, so now clustering unsupervised because it does not provide clear label. Unsupervised classification learning technique, machine learning technique. So they have the following variant. The K-mean clustering represented by centroid. Right, the standard algorithm is we currently use Hodgkin 1 algorithm. First assign each data point to a cluster, and then you seek to minimize the total within cluster variation, which is calculated as the sum squared Euclidean distance between any data point, such that between any data point to the centroid, such that and then you keep updating, such that the more percent of data point are grouped together, and then you keep updating until you find optimal position of this central. A hierarchical clustering, you work differently, but you first treat each data point as its own cluster. So if you have a total of 100 data points, so suppose you're working on a data frame of 100 rows and the beginning number of clusters is 100. Right? Treat each data point as a single cluster. Then you identify the two clusters that are closest together and merge the two most similar clusters all the way up until all clusters are merged together. So that the farther two data points apart, the most on the assumption that the farther two data points apart, the more dissimilar they are. On the other hand, if the two data points are closer, then they are more similar. They should be more similar. Now the logic of trend test split. So why should we do trend test split? Well, because if you use statistical models to learn some underlying information regarding the data, then your model fit well on the data, but there's no guarantee that the result can be generalized to all models. So you fit a really highly predictive model on the data, which the model is trained on, and then you use the model, say stock market model, to predict, say, for example, you specify a statistical learning model Taiwanese stock market data, and the model fit very well, and you have high predictive power. And then you use the same model to predict, say, the China stock market or the US stock market. You probably fail, right? You probably won't work as well. So easier way to go is overfitting. You derive or predict the model from the given data is to do trend test split before the estimation. To split the data into two parts, one for training, one for testing. The high proportion of data allocated to the training set, the more your model can learn from the data because you were able to see, right? To glean the distribution information from the data. If you set your testing data to be a higher proportion of the total data. But the model, of course, will be less generalizable, less flexible, right, to other data. Finally, about data leakage. The final thing about data leakage, some information trying to predict may inadvertently make their way to the training data and thereby reduce the utility of learning. Because you shouldn't, there's nothing more to predict. You already know the information. So what's the point of predicting? Right. So they kind of give you a false sense of confidence, which is not good. Right. But so after we do trend splitting, we need to validate our trend model on the testing data. So we need to do cross validation. So there are several variants. Then leave one out, cross validation. LOCV for data set N observation. We would use N-1 observation as our training set and validate the result, meaning that the model trained on N-1 observation on just one single lift out observation. And we would do this N top. Right? Then we take the average of LOCV estimate as our model MSE. K4 cross validation is just the same. It's almost like a simpler LOCV. Can we divide data into K part, K-fold, using the K-1 part to train the model. And then we use the train model, and we validate the train model on the left out part. And then, so which will give us K estimate, right? And then we take average of the K estimate as our model MSE. Alternatively, we can use Bootstrap. Bootstrap take a large number of random sample through repeated trial with replacement, of course. So we're averaging the result across all simple estimate as our Bootstrap SE. standard error. So the result should reflect the density of the data because it has replacement. So that if you see that like there are a large number of data points clustered around a certain range of the data, so they should have higher probability of being selected each time because the model allows for replacement. Right? So that if you can repeatedly draw lots of data points of a certain value, you know that the density region is probably bigger. So that this method can help us to detect the density of the data, so that we should know. So if you do a large number of bootstrap replication, you should be able to review the density of the data. For example, here is a high density region of the data. That would be useful when the data that we're working on are not normally distributed, like this one. So this is better than our sampling method. Our sampling method only rely on one draw of n number of samples. So this rely on n draw of n number of samples, so that it should help us detect the distribution of data, density distribution of data. And hyperparameter tuning. Hyperparameters are not estimated. They are assumed by us to improve model performance. And this can be achieved through tuning. So by setting a different combination of hyperparameter and feeding that iteratively into the model in order to find, to locate the combination of hyperparameter that has the lowest MSE. And that's the one we want. Now, get to so how to measure prediction accuracy. So there are a couple ways to measure that. The prediction, the most common one is the prediction accuracy matrix. So we usually do the 2x2 way. So there's a this is especially useful for model binary outcome, which there's only a true or false. So the first one is the actual class. The second one, so we need to compare our predicted class against the actual class from the data. So there are two, this should generate two types of error. The false positive type 1 error, meaning that you incorrectly reject a true null hypothesis. For example, a man, of course, current genetic science does not allow a man to be pregnant. Of course, in 10 years from now, I might be wrong. For the man comes to you, say, and then you diagnose the man to be pregnant. And that's typical type 1 error because you incorrectly reject a true null hypothesis. The underlying, say, the truth is negative, right? The man is not pregnant, but your result indicates that, oh, he's pregnant, it's positive outcome. So your test result wrongly indicate that actually false condition is present. But then maybe that false positive, meaning that you fail to reject a false null hypothesis. For example, a woman who's a big belly, obviously pregnant, and came to you, you say, no, you're not pregnant. So your prediction is wrong, but the truth is the woman is pregnant, so positive outcome. So the test result erroneously reject the presence of actual true event. So there are a couple ways to measure that. So, for example, receiver upgrading characteristic. ROC is a graphical plot that illustrates the diagnostic ability of the binary classifier, which is your model, your binary outcome model, has this discrimination threshold value. So what are those the combination of those discrimination measures? Well, the first one is the true positive rate, which is measured as the true positive over true positive plus false negative, which is used as the it should be the y-axis. I got something wrong here. I will update that. The true positive rate. True positive rate. On the y-axis and the false positive rate. On the x-axis. So if the model has higher true positive rate and lower false positive rate, say model 1. Model 2. The the model 1 is said to have higher predicted ability, predicted performance than model 2, because it has higher area under the curve, AUC. Then, because model 1 has higher AUC than model 2, okay? On the area under the curve. Finally, this semester we also cover text mining. So we can infer topic genre, the intention of the writer, and sentiment of the reader, or the reader from text data. And then the most basic unit of observation in the text data is a document. And then we read a large collection of documents, removing the punctuation, parsing, stemming, and using localization for each document to enter token, the word, and collecting them into a corpus for further processing. And our current workhorse model is the latent derivative application code, abbreviated as ODA. So the document may, of course, communicate multiple topics, but the word used in the document are related to each topic with different probability, so that they share mixed membership. So that's what the LDA is. It's a mixed membership generated model, right? So that each word is related to a different topic. Each document can also contain different topic with different probability. And then the model will generate this membership assignment first. So the document may relate to more one topic or less to other topic. So we need to use the following parameter interest. Is the distribution of topic, alpha is distribution of topic in document. Higher alpha means that the word is more mixed because, well, word may have higher probability related to multiple topic. Well, beta is the distribution of term per topic. Well, it should be interpreted in reverse fashion because if you have lower beta, that means there's a higher probability of clustering within a given topic. If you have higher beta, that means that the given words relate to multiple topics. And then in order to explain the term probability, we also need document term matrix and term topic matrix and document topic matrix, so that we can estimate the joint probability distribution that if we randomly pick a document D from large D, so what's the probability of that being related to a certain topic? It's given by the probability distribution, the joint probability distribution. And another domain of topic modeling, and there also much of research interest, is the sentiment analysis. Because we can, but to do that, we usually import some pre-coded sentiment dictionary. And in our working example, I simply use the Bing or Microsoft Bing or Google dictionary, sentiment dictionary, where you might want to define your own. And then we should simply look through each document in our corpus, and then the algorithm should identify each word in the document of that corpus, see if they contain those sentiment word in a pre-coded dictionary. And then you will sum up the total frequency from each category, and then after that, subtract the negative count from positive count to get a net sentiment rating for a piece of text. And of course, it can be measured as a binary coded, so long as the positive rating is larger than negative rating, then the document will be labeled as positive, otherwise it will be labeled as negative. Or it can be measured on a greater scale. For example, if you have more, say much more positive sentiment word, then negative sentiment word, and then you can say, okay, so this piece of text is more positive, the sentiment rating is more positive than the other piece of text. Of course, then you should also pay attention to the percent of block cloud, because you kind of change the direction of sentiment in the text. But of course, that's really hard to measure, right? So talk about it in class. All right, so this pretty much sum up the lecture part of this semester, and I hope you have learned a lot and You should be aware that most of the material here actually graduate level subject, so you should be proud of yourself. And we hope that you will also make use of your the data can account given to you to get yourself familiar with regular R and will do all this rather important statistical computing, and hopefully you will eventually apply those skills to your current coursework or your your work after you graduated. So so pleasure meeting you guys, and I hope that I have a chance of meeting you somewhere or other venue. So that's about it. Okay, so that's it.